you can increase the temperature, you also decrease the pollutants of these engines, which is obviously an important factor also. Now, one way to mitigate the effects of high temperature as well as hot corrosion is to use thermal barrier coatings. Here you can see this is the thermal spray approach to applying these coatings, and they consist of two layers. You have the bond coat metal layer, which is applied here between the substrate and the top coat, ceramic top coat. This bond coat does two things. It can protect you against oxidation or hot corrosion, and as well it acts as a sort of like a primer layer to give you better adhesion between the ceramic layer and the component. So you have a temperature profile here where you have a decrease in temperature across this insulator ceramic, and then kind of plateaus off because it's a better metal conductor. And a very important feature something that occurs relates to thermally grown oxides. We know that metals oxidize, and at high temperature, when you oxidize, you form what's called TGOs. You can have different types of TGOs that form. However, the best TGO is alpha alumina, dense alumina layer, continuous layer, that slows down further oxidation. It doesn't eliminate it, but it just slows it down so that you can extend the life of these components. You also, what you want to try to avoid is the formation of mixed oxides, nickel chromium oxides, because they tend to grow faster, and the thicker your TGO gets, the more strain it puts in the ceramic layer adjacent to the TGO layer. And failure typically occurs within the ceramic layer right next to the TGO. So you want to slow down the oxidation process, which means try to delay the formation of mixed oxides. What typically happens is you start forming these mixed oxides once you deplete your aluminum level within your metal bonder. You deplete it to a certain percentage, and then the kinetics is such that it forms these mixed oxides. This non-cryogenic milling of the powder, as I mentioned, liquid nitrogen is typically used for doing this. And the reasons are that metals are fairly ductile. So, we had a plan initially when we started this. We said, in what year we want to get to this without liquid nitrogen? It was extremely challenging. We kept getting this for 3.5 years. It's flakes. Because metal being soft, we were just pounding it, flattening it out. And also, liquid nitrogen also prevents oxidation of metal, right? Because what you're doing is you're milling it, and the metal powder is submerged in liquid nitrogen, so it doesn't see oxygen. We took some measures to address that issue. However, after 4 years, we were finally able to get equiax particles. And here you see X-ray diffraction spectra of the as-received powder and then the milled powder. And you can see that we have peak flattening, which is the direct result of the fact that you're refining the grain structure. Now we then took those milled powder, introduced it to a thermal spray process. In this case, it was the HVOF process. This work was carried out at the F.W. Gartner. And then we applied our coating. Here's our cross-sectional view of those coatings. And then when we compare it to the conventional coating of the same composition, we see that it's fairly similar. It has a slight increase in hardness, but pretty close hardness and relatively low porosity. We carried out some static oxidation, high temperature oxidation tests at McGill University. This is cross-sectional view. This is the top view, conventional nanostructured coating. And this was carried out 95 hours at 1,000 degrees Celsius in an air furnace. What you see is that with the conventional coating, you form a dark layer of alpha alumina as well as this mixed oxides. It's lighter. Whereas the layer that formed here is alpha alumina only. Now you see it's all broken apart, the layers, but that's because of the fact that you're putting this in a mountain. And you have different shrinkages, and so it will rip your ceramic layer, but these were continuous layers at one point prior to the process. We look at the top of the surfaces, and here you see polyhedral crystals, and those are mixed oxides that are present there, and there's absence of that. So we feel pretty confident that this is what we had, a constant alpha aluminum layer with no mixed oxides. One important test that is carried out by the gas turbine engine OEMs, the original equipment manufacturers, is the high temperature thermal cycle test. And here you see a Hastelloy X superalloy, 1-inch button, 1/4 inch thick. You apply 2 layers for the thermal barrier coating. We have the top layer. In this case, we went for all samples. They were atmospheric plasma spray, yttria, partially stabilized zirconia top coat. And here we see the HVOF nitroly bond coat. Half the samples were sprayed with the conventional powder and half with nanostructured powder. And each thermal cycle consisted of 9-minute ramp up, 45-minute hold at 1,093 degrees Celsius, and then you had a 10-minute forced air cool down. And you cycle it up over and over again until we had failure. Failure meant that we had over 20% of the surface, coating surface that has been removed. And these samples were not heat treated. A lot of the OEMs will heat treat their samples. It extends the life. However, we want to do a comparative test, and we weren't necessarily wanting to extend this too high because it just takes a lot of money and resources for us to do. We wanted to do comparative. So here in the dark column, this is the best result from using conventional bond coat TBC. This white column is the average of 3 samples with the nanostructured bond coat TBC. You see we have an increase of about 50%. That's pretty dramatic. That's good. We're pretty pleased with that. Failure analysis was carried out at the Naval Academy. And here's cross-sectional views. Once again, I mentioned that the failure typically arises within the ceramic layer here, adjacent to the TGO. And what you see is this lighter region is the mixed oxides, and then this dark thin line, that's the aluminum layer. What we really want is that line to be thicker, more continuous, and try to mitigate the formation of these mixed oxides, which is what we got with the nanostructured bond coats. You see, we have this thick alpha alumina continuous layer, and then we have a little, in this case, a little bit of mixed oxide there. Now, the reason for, we have a hypothesis on why this is occurring. The hypothesis is that there are also these nanodispersoids that are formed while you're doing the milling, while you're refining the grain structures. And their presence seems to do several things. They seem to help nucleate the formation, quick formation of alpha alumina, which is good. As well, it can decrease the effect of high temperature creep, which is a good thing for these components. But it's a very complex thing, mechanisms that occur within these. And we're certainly open to working with experts in the field to better understand this. So the feedback we got from the Naval Academy was that the thermally grown oxide on the nanostructure coating, thicker, more continuous alpha alumina layer, very few mixed oxide regions. For the conventional counterpart, a dual layer consisting of alpha alumina as well as the mixed oxide. And its overall thickness seemed lower. Typically, the TGO layer gets to a certain thickness and then you have failure. But it was obviously for